Welcome back to the last session. And so basically, now I am focusing on the complex field or algebraically closed fields and try to see what are the degrees of the representations, how many representations are there, and so on. So I will prove Schur's lemma, which it's a basic result concerning irreducible modules, and it will yield the degrees of irreducible representations, at least when the field is algebraically closed. It will prove that all only irreducible representations over an algebraically closed field of an abelian group are of degree 1, whereas the result is not true if the field is not algebraically closed. Even the cyclic groups may not have may have representations. Say if you look over rationals, if you take cyclic group of order 7, then irreducible representations, there are two irreducible representations. One is 1 degree and the other is of degree 6. All right. So what does this lemma says? That it tells you homomorphisms between irreducible modules, and it tells you that if V and W are two irreducible CG modules, and theta is a homomorphism from V to W, then theta is either an isomorphism or it is identically 0. And if you have a CG isomorphism between V is irreducible CG module, then it is a scalar multiple of theta is lambda times the identity on V for some scalar lambda. So basically for this, for the first part, I need not have C. It works over for irreducible FG modules. But for the second part, yes, definitely. I will need C or any algebraically closed field, or at least the field where I can have eigenvalues of theta. So how do you prove this? The proof is just straightforward, that suppose theta is not 0, V and W are irreducible. I am taking CG module, but simultaneously try to understand whether what happens for arbitrary fields. V and W are irreducible CG modules, and theta from V to W is a CG homomorphism. Then if theta is not 0, then I want to prove that it's an isomorphism, which is true because look at kernel theta and image of theta. Kernel theta is submodules of these are CG submodules of kernel theta is a submodule of V, and image theta is a submodule of V and W respectively. Now, theta is not 0 implies what is kernel theta? Kernel theta is not the whole of V. Theta not 0 implies image theta is not 0, but V and W are irreducible. Therefore, what do you get? That kernel theta, the only choice is that kernel theta is 0 and image theta is the whole of V, and therefore theta is on 2 and 1, 1, and therefore it's an isomorphism. Right? So for this, I have not used anywhere that C is algebraically closed. So this works over FGs. All right. So next, what was the next part, if you remember? The next part was that I take a CG isomorphism between V and V, then it is lambda theta V is lambda V. It's given by that. So theta I take from V to V, CG isomorphism. So you take an eigenvalue lambda NC, which is an eigenvalue of theta, and if your field is such that your linear transformation theta is a CG isomorphism, so it is also linear transformation from V to V. So you can talk of its eigenvalues. If your field is algebraically closed, yes, it will lie in F. But otherwise, suppose you have a linear transformation where the eigenvalue lies in F, then of course this will work. But otherwise, you go into a big enough field where you have the eigenvalues, then you need algebraically closed fields for that. Okay, so you take lambda, which is an eigenvalue, and look at theta minus lambda times the identity on V from V to V. It is a CG homomorphism. It's a CG homomorphism, and it is it's non-zero. Sorry, this is what? Its kernel is not zero, because lambda is an eigenvalue. So theta V is lambda V for some V, therefore its kernel is not zero. There is something in the kernel, and therefore the previous part says that it has to be identically zero. It has to be identical, because otherwise the first, it will contradict the first part. So theta is lambda times the identity on V. That's what it is. All right, so it's simple but very, very powerful. And what does this Schur lemma tells you? That if V is a non-zero CG module, then every CG homomorphism from V to V is a scalar multiple of. This is regarding the. I'm just telling you about the converse of the second part. The converse of the second part. Second part, look at the second part. It says that if V is irreducible, then theta from V to V is a CG isomorphism, then theta is lambda times identity. And this is the converse part. That suppose V is a non-zero CG module such that every CG homomorphism from V to V is scalar multiple of identity. So if 2 holds for every CG homomorphism from V to V, then V is irreducible. Okay. So how do you prove that? You prove, you use Meshke's theorem by taking a complement of, suppose W is a CG submodule of V, and you take W to be not zero. Then you prove that W is equal to the whole of V. So you take its complement, take W, and complement exists using Meshke's theorem. And you look at the projection from V to W by sending an element of V is W sum W dash, and you project this to W. And this is, of course, W. This is inside V, so I will say pi from V to V by projecting onto the W component, first component. And now it's a CG homomorphism. Pi is a CG homomorphism. And this is what? Every CG homomorphism from V to V is scalar multiple of the identity of V. If W is not the whole of V, this is not scalar multiple of the. How can this is a projection onto the first component? This is not. This pi is not lambda times the identity of V. because W is never lambda times V unless this part is 0. So you can produce CG homomorphism, which is not a scalar multiple of the identity. And so regarding the converse, one can say like this. So what does it tell you on representations? Okay. So it tells you that if you take a representation of G, suppose G to GLNC is a representation of G, then it tells you about the irreducibility of modules. Okay, the irreducibility of modules are connected with the irreducibility of the corresponding representations. So what does it translate into? The irreducibility of corresponding representation. You take a representation of G, then T is irreducible if and only if only n cross n matrices over C which commute with all Tg are scalar matrices. You know what is the center of GLNC? Scalar matrices. And you know that a matrix which commutes with all other matrices has to be a scalar matrix. But this says that the only matrices which commute with all the TGs are scalar matrices, then the representation is irreducible and vice versa. So it gives you necessary and sufficient condition on irreducibility of representations. And how do you prove that? How does it follow from that? Let me. All right. So okay. So let's try to prove this result that your representation is irreducible if and only if the only matrices which commute with all TGs are scalar matrices. How do you prove that? Suppose T from G to GLNC is irreducible. Then you consider the corresponding module. So what will be the corresponding module? It will be n copies of C regarded as CG module. As a C module, you are already familiar with how is this regarded as a C module, but how is this regarded as a CG module? G times V1. This is how I'm writing the elements of V as columns. This is your matrix TG multiplied with V1, V2, V. Now, T irreducible implies the corresponding module is an irreducible CG module. All right. Now, suppose you are given a matrix T which commutes with all TGs. So I look at this. Okay. So my aim was, I will go back to my question, that your representation is irreducible if and only if the only matrices which commute with all TGs are scalar matrices. Okay, so that was my question. So I started with an irreducible representation, and which essentially means that the corresponding module is irreducible. So which means that if I take Cn as a CG module via this representation, which is done like this, then this module is an irreducible module, right? So now I have taken a matrix which commutes with all TGs, then I want to prove that it's a scalar matrix. So what I do, that you look at this map from Cn to Cn given by this. Okay. Now, because of the fact that ATG is TGA, okay, this theta is a CG homomorphism. this is how you regard Cn as a CG module. Using this and this, it turns out, just a simple check, that theta is a CG homomorphism, but now theta is not zero if I start with the non-zero A module, and therefore theta is an isomorphism, because this is you apply Schur's lemma, and therefore theta is lambda times the identity on V. And so theta is lambda times the identity of V will essentially mean that your matrix A is a scalar matrix. Right? So this is how you prove, and conversely you can do the same steps backward, and you can prove the converse. Therefore this gives you a necessary and sufficient condition on irreducibility of representations. So let's apply this on D10 representation. I have just taken a 2-degree representation of a dihedral group of order 10. And look at this. So zeta is a primitive fifth root of unity. And so I map A to this matrix and map B to this matrix. It's a homomorphism from D10 to GL2C. And this is an irreducible representation. I can apply what I have just said, that this is an irreducible representation if every matrix which commute with all TGs, the only matrix which commutes with all TGs are scalar matrices. So I just took a matrix, and if it commutes with all TGs, then in particular it commutes with TA and TB. So as soon as it commutes with TA and TB, you can prove that A is a scalar matrix. So this is just a small check. And therefore, because the only matrix which commutes with all TGs are scalar, therefore this is an irreducible representation. So it's basically a representation induced from a linear representation of a cyclic group of order 5. So, but those things I will, since I have not talked of those things, induction and all, because we are just starting this, I said this is a basic course. So I will just from the ground, using this theorem, you have proved that this is an irreducible representation of degree 2 of D10. All right. Now, this Schur's lemma also tells you that irreducible representations of abelian groups are of degree 1, are all of degree 1. Why? Because of, again, I am the second part where you require C to be algebraically closed, or this works when if you replace C with any algebraically closed field, this will work. That you start with a finite abelian group G, and I want to prove that the only irreducible CG modules are one-dimensional over C. How do you prove that? Take V to be an irreducible CG module. Now you pick an X and G and consider T from V to V given by V going to XV. T is a CG homomorphism because G is abelian. G is abelian, T becomes a CG homomorphism. Now Schur's lemma tells you that because V is irreducible, T must be lambda identity of V, which means that XV is lambda V for all V. So every subspace W of V is a CG submodule, because this tells you what is the action of G on V. The action of G on V is X dot V is lambda V. Lambda is a scalar. Lambda is an element of X. So if I take any subspace of V, it becomes a CG submodule of V because of this property. Because of this property, any subspace of V becomes a CG submodule. But your V as a CG module is irreducible. It does not have any submodule, meaning that it will not have any subspace. So, which means that its dimension is 1. So therefore, this is C, or I replace with an algebraically closed field, then you get this. So what do you get is that if G is a finite abelian group, then every irreducible representation over an algebraically closed field must have a dimension 1. And then I also want to count the how many representations will you have. So basically, so what you have is just homomorphisms from G to C cross. These are all the irreducible representations. And another consequence of Masheke's theorem, now I want to count the non-isomorphic irreducible CG modules. And I want to have an understanding of the degrees of those irreducible representations as compared to the order of the group. And so those who know representation theory, they know the answer to this, that the number of irreducible representations will be the number of conjugacy classes of G, and the degrees have the relationship. But these results, which I am going to do now, they can be modified when your field is not algebraically closed, but then you have certain more notions and so on. So instead of conjugacy classes, you have the concept of F conjugacy classes, rational conjugacy classes, real conjugacy, whatever field you are working with. But I am just working with complex numbers for the sake of simplicity. So what one of the main result, basic result which you prove is that if U1, U2, UK form, how do you get irreducible representations? You get irreducible representations from irreducible modules over FG, or I'm talking of irreducible CGs. So, and you get equivalent representations correspond to isomorphic modules. So that means if I take a set of non-isomorphic irreducible CG modules, then the corresponding representations will be that. So if U1, U2, UK form a complete set of non-isomorphic irreducible CG modules, the first question is that why should this be finitely many? I will also answer that question. This form a complete set of non-isomorphic irreducible CG modules. Then the dimension of UI square is equal to the order of G. So maybe in terms of representations, if I say T1, T2, Tk are all the irreducible complex representations of G, then you take the degrees and take the squares and sum. It is equal to the order of the group. All right. So, and if G is abelian, what does this read? All UIs are UIs are irreducible CG modules, so the dimension over C is 1. So this tells you that K is equal to dimension UI over F is 1. C, I will, since I am writing C here, so let me write C here. This is 1. If G is abelian, these are ones just now we have said. So what you get is that K is equal to the order of G. So you have as many one-dimensional representations as the order of the group. And so if G is abelian, there are precisely order of G irreducible representations of G, and each of degree 1. All irreducible, if G is abelian, then all irreducible representations have degree 1, and there are precisely order of G of them. This is a consequence of this, but let me try to prove something in this regard, that I want to have a control on non-isomorphic irreducible CG modules. How do I obtain? Basically, you regard CG as a CG module I'm regarding CG as a left CG module. Actually, this is also, this way also you get that the regular representation is sum of other irreducible representations, each occurring its degree times that. That result, regular representation is a sum of irreducible representations, each occurring its degree will happen when you are working over complex, but otherwise that result will still hold, but each occurring how many times will change. That was one question which somebody asked yesterday. So maybe I will describe that when I break the regular representation. Okay, so let's try to see CG, regard CG as a CG module, left CG module I'm talking of. And I know that using Macheke's theorem, I can write CG as a direct sum of irreducible CG modules, because I have taken characteristic 0 to be on a very, very safe side. So, or if you take algebraically closed field, then you take its characteristic to be co-prime to the order of G. Again, the same thing you will do. So you break CG as a direct sum of irreducible CG modules. Then this says that every irreducible CG module is isomorphic to one of the UIs. So therefore, in order to write down irreducible representations, what do you need? You need irreducible CG modules. Now, where do you go to get hold of those irreducible CG modules? You go to this irreducible CG submodules of CG as a CG module. That is enough. Okay. So you if you break this as a direct sum of irreducible CG modules, then up to isomorphism, you will get hold of arbitrary irreducible CG modules. Every irreducible CG module is isomorphic to one of the CIs. So it is enough to have these ones in hand in order to write down irreducible representations. So I will prove this. I will prove this step, and maybe some part I will, for this step, maybe I will leave something for you. And then next part, what I do, now you have written CG as a sum of irreducible CG modules, and you prove that every other CG module is isomorphic to one of these UIs. Therefore, all you need to concentrate is on the representations corresponding to these UIs, or these UIs as irreducible CG modules. Now, out of these U1, U2, certain groups are isomorphic, and certain. So there are some copies of U1, some copies of U2, some copies. So I assume that the first U1, U2, UR are non-isomorphic, and the rest of the UIs. So this is my CG. This is my CG. This initially I wrote this in some manner as a direct sum of irreducible CG modules, but these some of these may be isomorphic to each other. So I just write down the first ones which are not isomorphic, and then the rest ones are isomorphic to one of these. So that means I have certain copies of U1, certain copies of U2, certain copies of UR. So this step says that how many copies of U1 will come? Dimension of U1 over F times. So this is C. Dimension of U1 over C times. Here again, C algebraically closed field is used. Otherwise, if your field is not algebraically closed, then this is not this number. How many times it is repeated is not this. Is not this. This will be less. Okay. So that change will be there if your field is not algebraically closed. All right. So in the this step, so what you prove is that U1 is repeated precisely these many times. The dimension of U1 over C. U2 is precisely repeated these many times, and UR times. And now once you have done this, you take dimension over C. What do you get? On the left hand side, I get order of G. The dimension over C is the order of G. On the right hand side, what do I get? Dimension of U1 over C. Then dimension of U1 over C, how many times? It's plus dimension of C plus dimension of C. So that means I am taking its square. Okay. Dimension of U2, C square, and so on. So what you get is this, taking the dimension over C on both sides, what I get is this. So this is the result which I am interested to prove. So this result is basically a combination of these two steps. So let me start with you, and then you can continue. All right. So in the first step, I said I want to prove that if U is any irreducible CG module, then U is isomorphic to one of the UIs. So as a first step, so case 1 you take, I take that U is a submodule of, U is a submodule of, and then in the next part I will take U is an arbitrary irreducible. U is a submodule of CG and U is irreducible. So we will prove that U is isomorphic to UIs. All right. How do you prove that? Consider a non-zero element of U. You take as a non-zero. U is irreducible. Zero modules you don't regard as. Okay. So you take a non-zero element of U. Then you assume that you write U as U1 sum U2 sum UM. And you assume that UI is not, some of the UIs is not zero because U is a non-zero element I have taken. So you take, so if I look at the projection pi I of CG to UI, then look at its restriction on U. So what I get, pi I from U to UI, it is not zero. Because I know that there is some element of U whose projection to the ith component is not zero. Therefore, but because both are irreducible, therefore this is an isomorphism. This is a non-zero homomorphism, and therefore this is an isomorphism, and so U is isomorphic to UR. So if U is a submodule of CG, then U is isomorphic to one of the irreducible submodules which occur in the decomposition of CG as a sum. Okay. And then in the case 2, I will take arbitrary one. Case 2, I will take U is an arbitrary irreducible CG module. And then I will prove that I want to show that U is isomorphic to one of the UIs. All right. So you take a non-zero element of U and you look at the submodule of U. U irreducible implies this is non-zero because this is a non-zero. U is a non-zero element. U is irreducible implies that U is equal to CG. So it's a simple module generated by this U. And now you define this theta from CG to U by mapping alpha to alpha times U. And theta is a CG homomorphism. You can check. And theta is onto because U is CG U. Theta is onto, and therefore CG modulo the kernel of theta is isomorphic to U. But now kernel of theta has a complement because of again Mashake's theorem. So I will just write down here. So CG is equal to kernel theta plus another submodule of W is a CG submodule of CG. Because of Masheke's theorem, it has a complement, and therefore CG mod kernel theta is isomorphic to W. So U is isomorphic to a CG submodule of W, and now you apply your previous case that an arbitrary CG module, an arbitrary irreducible CG module is isomorphic to a CG submodule of CG, and therefore it is isomorphic to one of the UIs. And now I think the next part it's little more calculation. So maybe those interested can read the textbooks, and that this occurs precisely these many times. And by computing the degrees, you get this. Okay. Now, how much time I have? Okay, so I have to, and in 10 minutes I will wind up, and then maybe I have to yet introduce some characters, and I will just state the results in characters, important some results, and then you can continue reading the stuff on your own. All right. Now, how many irreducible representations? As many as the conjugacy classes. How do you get that? How do you get that result? You get that result from what I was saying here. CG is isomorphic to U1 direct sum with U1 some number of times, its dimension times, then U2 sum U2 some number of times, and then some UR sum UR its dimension times. Now, as I said, once I have V as a decomposition into submodules, then the corresponding effect comes on the representations. Now, if I take representation of CG as a CG module, then I will be regular representation. And now you take representation of U1, call it T1, and then again representation of U1, call it T1, T1. How many times T1 will occur? As many as the degree of T1 times. Degree of T1 is the dimension of U1 as a vector space. So it is this, then degree of T2 times, and then degree of TR times. So the regular so if I go to characters, then I will say that a regular character is direct sum of is sum of irreducible characters, each occurring its degree times. A regular representation is equivalent to that. Okay, so my aim was to tell you on the conjugacy classes, right? So I will first say that. All right. So what you can prove, Vedaban and Artin proved a very beautiful result that each of these UI direct sum with UIs is isomorphic to, it's a simple ring. If you take in the decomposition of CG, if you take those UIs which are isomorphic, then this is, in the beginning, it's a left CG module. I'm taking direct sum of left CG modules, but it's a two-sided ideal of the ring CG, and it is isomorphic to a matrix algebra over a division algebra, but because I've taken an algebraically closed field, it will become isomorphic to MNIC, where NI is the dimension of UI over C because of the algebraically closed field. If your field is not algebraically closed, the only difference will come is that this U1 will not repeat dimension of U1 over F times. This will change. This will change, and then MNI over C will get replaced with the matrix algebra over a division algebra. So the theory is slightly more involved, but this is just MNICs. So if I use Wedderburn-Atten and theorem, then what you have is that this is Mn1C direct sum with Mn2C direct sum with MNRC. What are NIs? NIs are the dimension of UI over C. I'm using algebraically closed field. I'm using Wedderburn-Atten theorem on the structure of simple Artinian rings and, of course, semi-simple rings. And now you take the dimension over C. Now you take the center. Center of CG will be isomorphic to the center of this is scalar matrices. So scalar matrices meaning that it's isomorphic to C, and it's isomorphic to C, R times R is the number of non-isomorphic irreducible CG modules. And then this you can prove that its dimension over C is the number of conjugacy classes. So there is no page after this. So this dimension, its dimension over C, dimension of center of CG over C is equal to the number of conjugacy classes of G. So basically you can prove that if you take G in G and denote by this its conjugacy class, and take the sum of all the elements in this conjugacy class, and I will denote this by CG. CG means sum X in the conjugacy class of G. These are elements in the group ring CG, and what you can prove is that it's a basis of center of CG as a vector space over C. And so you has as many elements in a basis as the number of conjugacy classes of G, and therefore the dimension of the center of CG over C is equal to the number of conjugacy classes of G, and therefore your R will turn out to be the number of conjugacy classes of G. So you have those many representations. And now I'm quickly going through I will just write down some results on the corresponding. Yeah, there was one question in the previous lecture on Mashique's theorem that if where is that? Yeah. So I will just I try to write down. Yeah. So if the characteristic is 0 or co-prime to P, I said this is a sufficient condition for this to break, but this is also necessary. And just to give you one example, since we just talked about that, maybe I can erase this, or maybe I will write down somewhere here. All right, and let me write down some example which I worked out. You take a cyclic group of prime order. Take G to be take G to be cyclic group of prime order, and you take field to be field with P elements. Now the characteristic is not co-prime. Look at this representation from G to GL2F given by A going to 1, 1, 1, 0. This is a 2-degree representation. And you look at the corresponding module. Module will be, your V will be F2. F2 regarded as FG module via this A dot alpha beta will be alpha beta. And what you can prove is that this subspace, if I take this 0 belonging to F, is the only one-dimensional subspace of V, which is an FG module, which is FG submodule. This is the only one-dimensional subspace of E, which is an FG submodule, and this does not have any complement. And you can prove this, and therefore, so this result will not hold if this condition is not met. Okay, so I am quickly moving to something. Just 2 minutes I will spend, and then maybe you will have your question answers. So I will this one. All right. So what's a group character? This is you have the representation now. As I told you in the. Okay, so you have this representation and G to TG, and then you take the trace of this matrix. It's called character, and degree of the character is same as the degree of the representation. Character is called irreducible if the corresponding representation is irreducible, and characters corresponding to the characters are constant on conjugacy classes, because if I take G and H, which are conjugate, then if G is conjugate to H, then TG and TH will be, they will be similar matrices, and similar matrices have the same trace, and therefore characters are constant on the conjugacy classes of the group. And so you just need to compute characters on representatives of conjugacy classes. They are constant on the conjugacy classes. I will just skip this. Degree of the character is the degree of the representation, and trivial character degree 1 is called principal character. And linear character means characters corresponding to linear representations, which are homomorphisms, but in general, characters of degree more than 1 are not. So they are not homomorphism, because you're taking trace, and trace is not multiplicative. So how many linear characters or irreducible representations? Because of the fact that when G is abelian, you have the order of G irreducible characters, and all of them are linear. So in general, for an arbitrary group, what you will get, answer to this will be the index of G dash in G. And maybe I will, I don't have. So for example, if I look at S3, then its commutator subgroup is A3, and you have 2 linear characters, 2 linear representations, and similarly for you have it for AN. And so I think I will. So this is the character table of the group. Maybe I will. Yeah, if you break a representation into direct sum of irreducible representation, then you have a corresponding breakup of a character into irreducible characters. These are called constituents of, these chi-i's are called constituents of that character. And arbitrary characters from irreducible characters, because you get arbitrary representations from irreducible representations exactly the same way you get arbitrary characters from irreducible. So basic importance is about the irreducible characters. And so maybe I will stop here while defining the character table of the group. That I'm just defining it for you have as many characters, irreducible characters, as the number of irreducible representations, which is the same as the number of conjugacy classes. So R is the number of conjugacy classes. So on one side, I label conjugacy classes, and these characters are constant on conjugacy classes. So I will just write C1 here, C2 here, CR here, and A1, A2, AR are representatives of the conjugacy classes. CIs are the conjugacy classes of the group. And so this table, I will just write down these values. So basically you are encoding all the values of the characters, irreducible characters of G into this table. And this table is called the character table of the group. There are orthogonality relations and very interesting things, very interesting study of these characters. And these characters are character values are algebraic integers, and so on. So chi of G, and what is the relationship between chi of G, G inverse, and so on. So various things, and using the properties of these characters, Burnside proved that a group of order P to the A, Q to the B is solvable. It's not simple, he proved. Yeah. So I think I will stop here, and because there will be questions. So my main aim was to just to initiate those who are new to the subject, those who knew the subject already. So maybe this was too elementary. But my aim was basically to initiate students into the subject, and if they are interested, they can read it from the masterpieces and develop further knowledge into the subject. So thank you. I think I'll stop here.